Oh, yes,
How
still.
how how did you model the manual cross bonding, the actual cross bonding? Can you show me just quickly? Not like model it, but just maybe you have some model or something.
Yes,
You can
yes.
take me through that. Because why I'm saying that is because it's sometimes a requirement to calculate
Okay.
uh, the sheath standing voltage or the sheath circulating current in the cross bonded system.
Yes,
So
yes.
I do that in CDEX, but I just wanted to know whether when you do that work, do you put like a sheath voltage limiter in the model or you don't put it?
No, no, we don't put that and all. But I will show you how we used to model the that system. Okay.
Okay.
Just
Okay.
wait a minute. I will open that file. I will open
Yeah,
that.
yeah, please. Yeah, yeah. And another thing, Venkat, is
Yes.
how do you combine say there is a load, there is a source light, any voltage source, and then
Okay.
there is a overhead line, and
Okay.
after that overhead line, then the cable, and then there is a load. So how do you really join these two pieces together? Is there a way to do that? This subject is of
Yes.
very high importance to me, is because
Yes. Yes.
in UK we get that kind of line a lot, right? And
Okay. Okay.
there are two type of installation on at the junction of overhead line and cable. One is
Okay.
called
Okay.
cable ceiling and platform, and I will show
Okay.
you that as well how it looks.
Okay.
Uh, and the another one is called a cable ceiling and compound. So that
Okay.
when it's called compound, it's more or less like substation.
Okay. Okay. Fine.
So
Okay.
we treat them as a substation, and sometimes what we need to do, nobody asked me, but sometimes what happens is that when the guys do the earthing,
Oh,
they install the earth rod as a separate. They don't connect it to the mat. So I am interested to do some research on that. So that's why I'm asking.
okay. Okay. Then we will see that how to join a cable and overhead line in the upcoming session.
Yes,
Okay.
please.
Now I will show
That would
you
be lovely.
that part we can take it as a separate section. Oh,
Yeah.
okay. Then it will give you some more idea. If you have any doubts, that also we can clarify. But I will show you how we used to model the cable with cross bonding
Yes.
system.
Yes. That
Okay.
would be great. Yes.
Uh,
Yes. You even that overline stuff, you don't need to like show me step by step, but you just show I know how to model overhead line, and you can show me like how to put a cable and
yes.
together. That's it.
Yes. Yes.
That's what I wanted to know. And once I do that, then I will have uh,
Okay.
some level idea. This I am also publishing one paper uh, which was due actually 2020, but
Okay.
because of Corona, the conference didn't go ahead. But it is
Okay.
not on the the high frequency or switching stuff. It is just based on this power
Okay.
frequency stuff.
Okay. 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 Just
Yeah.
yes.
When is your festival? Is it tomorrow or today? Today as well.
No, it is tomorrow. It is tomorrow. It is
Tomorrow.
not a
Okay.
festival, as I said. It is not festival. It is a some special day. They used to go for their native temples to get like we used to go for temples and get what we say that a blessing from God. That is what they used to say. Okay,
Okay.
tomorrow is a good like Indians Indian culture. There is something now we have to visit
Yeah.
some
Yeah. Of
temple
course.
like
So
that.
is that like is that is that what I was saying is that allowed to you in the COVID like to go temple?
Yes, yes, it is allowed here. Because here all the restrictions have been lifted. I hope
Oh,
for
nice.
4 months back itself it has been lifted, so all the peoples are enjoying like
Okay.
all peoples are enjoying, man. They
Like normal, eh?
don't yes, they don't like what do you say, that they won't be concentrating like that and all. There is
Yeah,
COVID like that and all, there is no serious situations like that, they will act here.
yeah, yeah, yeah. Nice. It's good. At least somebody is getting some rebate.
Yes, yes.
We don't get that rebate.
Okay.
Here is I can't go outside. I mean, I can go for walk and exercise and stuff like that, but like I can't just go anywhere in the country. It's
Okay.
happening from next month, and they are saying they will try to
Okay. Put a lockdown there.
yeah try to ease lockdown. So there are various level 4, level 3, level 2, level 1. So
Okay.
so now at the moment the whole country is in level 4, which means
Okay.
there are so many restrictions. And
Okay.
after some time, then it will be level 3.
Okay.
Yeah.
Can you see this? I'm just modeling a cable. Okay.
Yes. So that's
Mm,
cable, right? Yeah.
yes, the same model which we have used yesterday. Okay.
Yeah. Yeah.
If you
Yeah.
have any sheath, then you have to, as I said yesterday, you have to put
Yeah.
sheath on this particular cable.
Yes.
Okay.
Yes.
Now, if you are going for an, what we say that now if you are going for an, like you have asked for transmission, right? You have asked
Yes.
for ideal transmission of cables. Then what we have to do is like we used to take this as a single set. Okay.
Okay.
Uh,
Yeah.
then this as a second set.
And you
Okay.
manually transpose them, eh?
Yes, yes, this is in third set. And then
Yep.
what we have to do is like we have to manually transpose this, right?
Yes.
Like this
I
we
get it
have
now.
to, mm, like this we have to join it here. Okay. And
I
what
get
we
it.
have to do is like, then what we have to do is like here we have to the second phase, then we have to go like this we have to do
Yeah.
manually.
Yeah.
Yes.
I got your point. Like, how do you cross bond them? But you know how they are actually cross bonded on
Uh,
the joint way. Want me to show
uh,
you?
oh, okay. You have that model? You have that model?
No, no, I don't have model, but I have the real photo. I can show you.
Okay, okay. If you have anything, please show me. I haven't, as I said, I haven't been
I
home
will,
to.
I will, I will show you in this. I will tell you in the same screen, like what it happens. So
Okay,
first I will share my screen and then I will talk you through your screen, right? Because
okay,
this is really important. If you do that, it will be good for you as well, right?
okay.
So
Yes, yes, yes.
so in the joint bay is a junction where two cable meets, right? Either
Yes.
they are deliberately put there. So
Uh,
this is like a box. So this R
okay,
phase comes in, this is comes in, right? I'm not
okay.
talking about transposition, I'm talking about cross bonding, right?
Cross bonding.
Then
Okay,
this is another piece of cable. So they
okay,
cable are jointed here, and this is a sleeve.
okay,
After putting the junction, this is to protect the cable sleeve,
okay,
right? And
okay,
this is
okay,
for another one, this is for another one. Then what they do, they took these sheath from here using these bonding cables, right?
okay.
These bonding cable away, and they
Okay,
put that in particular box. It's called link box, right?
okay. Link box. Okay, okay,
Yeah,
okay,
and I will show you how that looks, right?
okay,
Because I've done a lot of work and research on this. So
okay,
cable joint bay, right? So if you open the link box, so this is how it is covered generally, uh,
okay.
right? Inside, below the soil, right? And you see
Okay,
these three phases are coming in. Sometimes
okay,
they have a color tape, which one is RYB, right?
okay, okay. Yeah, got it.
Now,
Yes.
now this A comes in, right?
Okay. Uh-huh.
Here,
Hmm.
then it goes to C back,
Okay,
right?
okay.
Then B comes in,
B comes in.
it goes
Okay,
to A and becomes
okay,
A, right?
okay,
And
okay.
then this B itself become C, right? So
Oh,
you
yes,
seeing
yes,
here, you seeing
yes,
here, and
yes.
these are called links. This
Okay,
is these are called bonding cables, and
o-
this structure is called sheath voltage limiter. It is like underground surge arrestor, right?
okay, okay, okay.
So
Ah,
this is what it's called cross bonding, right? What
yes,
happens
yes.
is, yeah, right, what happens is in your route when you
Uh,
when you when you have like a, For example, I don't have that tool, but for example, this is your route, right? And then these are the junctions, right? Cable. So
Okay.
in each junction you got like a V-link box here, right? And that with
Okay.
SBL, and then that's earth. So this another cable here, third cable E is
Yes.
goes to basically a particular place, and that
Okay.
place is this dotted conductor is an earth mat to protect this joint, and
Okay.
this also protect a person operating this, right? So
Okay.
this is what it is, right? And
Okay.
this is how it looks like below ground and everything like that, right? See these
Okay.
cables coming in here and then going
Yes.
back,
Yes.
right?
Okay.
Depending on double circuit, single circuit, anyway, right? So
Yes.
then
Yes.
what happens is two link box will be like this, right?
Okay. Okay.
With SBL, and third one will be solidly earth, which means in that the only
Okay.
difference will be where did I put that photo? These SBL won't be present. It will be like, and these crosslink won't be present. Directly one, directly two, directly three, and direct to
Okay.
earth bar without these SBL, right? So
Okay.
there are two type of bonding. Either if if your cable,
Oh,
say you got a cable, right, and that
okay.
exactly 1200 meter this, if you
Okay.
can divide 400 400 400
400.
400 meter, right,
Okay.
then what
Uh,
happens is every box will have
okay.
SBL,
Okay.
and this box will also have SBL just on the junctions. I will
Okay.
also show you one diagram, and this
Oh,
box will
SBL.
have
What SBLE means? This is the both. That
sheath
is the
voltage
ceiling
limiter.
sheath.
sheath
Okay.
voltage
SV.
sheath,
Okay.
sheath
SVL.
voltage
Sheath
limiter.
voltage limiter.
Yeah,
Okay.
this
Okay.
is this is
Okay.
the SBL, right?
Yes. Yes.
this
Right.
is
Right.
this is just a surge arrestor but below
Okay.
ground, right?
Okay. Below
So
ground. Okay.
yeah, so this is what it is, right? Now
Okay.
if you can't divide this whole system in
Uh,
equal distance, which means is 400 is 323 it is 500, right? Then
yes.
what you do is first two cross bonding box will have SBL, and third
Okay.
will be directly earth to the ground,
Direct.
and
Okay.
these
Okay.
are earth via SBL. So you can see before the cable screen goes to earth, there is an
Yes.
insulation between them, surge arrestor, and it will
Yes.
operate only if there is a problem with cable, right?
Okay.
And
Okay.
it will operate to protect the joint. Now
Okay. Then
how
it will be directed to the towards the ground.
yes,
Okay. Then
yes,
yeah.
yes, and
Okay. Okay.
yes, and how it looks without a, I don't think I have. So basically, this is how
Okay.
it will look without joint. So ignore these, just ignore, like these are not. So it will be like don't bond it there, bond it
Okay.
there, bond it there. That's a called box without bonding links, right? And this
Okay.
is with bonding links. So we do earth check and stuff like that. So
Okay.
yesterday your
Okay.
mate was asking this. Now what happens is I will show you. I published a paper. Right? I will show you. So in that there is a diagram, or maybe one second. Uh, I think paper will do. Uh, this is my totally personal stuff. Like I do this final copy. So that's what it was. I done like the study, but not just like as a
Okay.
a high frequency or something. But this is a reason I have a passion to do it, right?
Okay. Okay.
So consider this, right? So
Uh,
here is a circuit between A to B substation.
okay.
So
Okay.
this denotes sheath earth via SVL, sheath earth
Okay.
via SVL, and that's basically directly earth, right?
Okay. Got it. Got
And
it. Yes.
as
Yes.
again SVL directly earth, SVL
Okay.
directly earth. So this is
Directly.
my
Yes. Okay.
handmade diagram, but there is also now what happens is sometimes these lines are made such
Will
between the
be
ABC
interfaced
substation.
with the cable. Yes. Yes.
Yes, so this place
Okay.
is called cable ceiling and compound. If
Okay.
it's a compound type, it's like if it looks like substation, and
Yes.
it can also called cable ceiling and tower, and I will show you what is the difference between them, right? So
Okay.
if I go back, if I go back to my this is of like personal interest to me other than learning insulation
Rather
coordination.
than
So
clearing. Okay. Okay.
so right, so this is this is a compound, right? So you see
Okay.
the line terminates here, but you can't
Okay.
see, but yeah, but you can see this is tower, and this is like whole
Uh,
like a substation. So these are surge arrestor, right?
okay.
And and you can see that line terminate, and after this place, it just becomes a below ground, right? Below
Okay.
ground line.
Okay.
So this is like a whole like substation. So that's why this
Okay.
is called ceiling and compound, right? And
Okay.
this is treated as a substation, right? As
Oh,
a whole. So
okay.
this is a whole,
Okay.
right?
Okay.
In earthing study, we have to treat this as a substation, right? Not like
Subs-
a supplementary thing, right?
Okay.
So this is what it is. Now, when I talk about a ceiling and tower, so
Oh,
this is how the tower looks. So
okay.
basically, this tower has a some kind of arrangement here on the top.
Mm.
So it depends on whether it's single circuit or double circuit. You see
Oh,
the
yes.
phases are terminated here with insulator. There are surge arrestor, and
Yes.
then and then uh, and then they got like these metallic sleeves. So the
Okay.
cable comes down through these, and after that the all route become underground, which I am showing you here, right?
Okay. Okay. Okay.
Now what happens here on this particular place
Okay.
is if they got the earth mat, if they got the earth mat like that, right?
Okay.
They don't do it in these tower, but sometimes they do.
Okay.
Now on these tower, right?
Oh,
If this is a thing, there are surge arrestor, right? What they
oh,
do is a surge arrestor. These are using 4.8-meter rod to the ground,
okay.
right?
Okay.
And they don't connect this surge arrestor earthing to
Oh,
this earth mat,
okay.
right? They think
Okay.
like, yeah, you want to put a rod down is fine, but then my argument is you also need to connect this earth and this earth together because it's same there. You can't isolate them, But
Okay.
sometimes the people don't do that, and they
Ah,
in
ah, ah, ah.
in these type thing they do. But when they
Ah,
got like pole without any earth wire, just three phases,
okay.
it comes
Ah,
like that. It goes on a mat, a small
okay.
mat here to protect the
Okay.
people. And then what they do is their surge arrestor comes like that, and they are
Ah,
grounded in right in the middle, but
okay.
not bonded left right. You know what I mean?
Okay. Yes. Yes. I got it.
Yeah.
I got it.
Yeah.
Yes. Yes.
So that's what I wanted to know as a my research
Oh,
point of view on after some time, like when I do this work. So I
okay.
wanted to know like what happens if I bond surge arrestor to the mat. In based on my earthing calculation, it will favor both lightning
Okay.
and switching or
Okay.
whatever.
Lighting and
And
switching. Okay. Okay.
but but what the cable engineer have an argument that if they bond if they bond their surge arrestor to this earth mat here,
Mm.
these surge arrestor here, so they are saying the cable are also connected like that cable
Mm.
sheath. So they are
Yes.
saying it damages the cable sheath, but in my
Okay.
understanding that if the surge arrestor is bonded down,
Oh,
it will still damage the sheath, I think,
okay.
because
Okay.
there will be a voltage difference between the
It
sheath,
will.
sorry,
Uh,
this earth and
uh,
the sheath earth, right? This
okay.
mat.
Okay.
So it is going to create a potential difference, and more current will
Different.
flow there. Maybe if you bond them together, then what will happen
Okay.
is it it will still transfer, but it won't create any stress on that cable jacket, I think.
Okay. Okay. You are saying like when this cable and the transmission line has been both connected through a same what we say that a mutual earth mat, then there will be no such incidents will happen like that. You are saying. Am I
It will
correct?
happen. It will still happen, but I think the problem will be less.
Less. Okay. Okay.
Yeah,
Okay.
the lesser damage will be on this part compared
Part.
to
Okay.
just
Okay.
arresting them like that,
Yes.
right? that's
Generally,
that's what.
what they do is like I have seen systems like uh, there will be transmission line, and from the transmission line it will be terminating in a cable, right? As you said now, okay, it will be terminating in a cable. But what they say is like there will be a surge impedance difference between the transmission line and the cable.
Cable.
Okay.
Yes.
Uh,
Yes.
and what happens is like there when this both comes into act, what happens is like there will be a rise in voltage. Okay, due
Yes.
to this, whenever there is an transient happening in the system, there will be a rise in voltage. So that what they used to do is like they used to put an surge arrestor in that location
Yes.
to minimize that voltage, like you said. Now,
Yeah,
yes,
that's
yes,
what
that
that's
is
what
what
I
the
am
situation
interested
is.
in.
Yes, that is what I have learned, but don't know that this much conceptually.
No,
Yes.
I do this. I am presenting a paper on this conference, which was
Oh,
last year meant to be,
oh,
but
okay.
it's now postponed. So I will then it was transferred to this year. But again,
Then, okay.
there is a problem. So quickly. So this is a conference. So I'm trying to illustrate some safety issues and based on my previous paper, and like tell them like what it is and how it is and various type of current and you know
Uh,
these things. So that's what I'm trying to illustrate, like
okay.
what happens in the high frequency fault. And uh,
Uh,
yeah,
yes,
so
it is really
that's
it is
yeah.
really a new zone for me. The things which you are working on.
No,
Yes.
it's not like I am working. I can do the job and I can go like home and enjoy. Like,
Okay.
but what I think is, you really need to do, something different, and you really need to make difference.
Okay.
So
Yes. 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 It is
so
necessary. It is
I
necessary
I
in a
believe
real
in
time.
I believe in that policy. So I can
Okay.
put my personal time, but I will get answer. I am that kind of guy.
Okay.
So
Okay.
this is a paper I published in Segre. So I published two of them. So
Oh,
one of them is basically the people follow the British standard, and
oh
one local
yes.
standard is called ENA standard. So it
Okay.
shows what are the drawback of that standard, what is not covered there, and what
Okay.
should be, for
Covered.
example.
Uh-huh.
Yeah,
Uh-huh.
yeah.
Okay.
So that tells that, and there's another one I published in electromagnetic interference and stuff like that. But yeah, the main point of this was to, you know, show you
Ah,
this
so
SVL thing, especially this.
yes. 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 Sheet
Yeah,
voltage. Yes.
yeah.
Yes. Yes.
And this is
Yes.
whatever you are modeling is you are modeling. Okay, you can share me your screen, then I will tell you. I will stop sharing.
I hope my screen is visible.
Not yet. It's loading.
Okay. Is it now visible?
Yes. Yeah.
Ah,
So what happens is when you are bonding between those two cable, your cursor is there. Yes. Yes.
mm, mm.
There will be a earth, and that will be jointed down. Using the
Okay.
wire.
Okay. As you
So
said now,
bet-
you have shown the
between
image.
between those two, yeah, between two particular cable, yes, here,
Okay.
yes, yes, they all the conductor will go forward to each other, whether transposed or untransposed, but then this all sheath will be come down and go to a link box, and that link box will have surge arrestor on each
Charger.
junction where you have the
Okay.
blank. Yeah, but yeah, I get your point now. On
Yes.
this one, and in any tutorial, if you can show me how do you really model the uh, a line,
Okay. Transmission line and
not line, but it's basically how you combine them. That's what I meant.
okay.
Because you told me how to model over a line, you told me how to
Yes.
model the cable,
Yes.
so
Yes.
all I need to do is join them. So whenever you get chance, you can maybe think about it and show me a case.
Yes, I will.
Like,
I will show you. I will show you because I don't think I have that project in my hand because we have uploaded this in the server. Then we used to free up spaces in our laptop. I will
yeah,
take
yeah,
that file. I will show you in the next session. Okay, for sure.
yes,
I will
yes,
show
please,
you in
thank
the next session
you. Yeah,
how we have joined the cable and the transmission line. But it won't be much difference. But there you used to do some what do you say that in real time you can see that much difference in bonding cable and transmission line. But here what we used to do is like we used to do generally join with an what do you say that the same the point we used to do join the both the cable and the transmission line. That's it
yeah,
what we used to do. Okay, that I will show you. That's not an issue. Okay.
yeah, yeah.
Yes. 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 Okay.
That would be great.
Yes, I will show you how we used to model that transmission line and the cable. Yes, I will show you. Yes, and then the part which I planned for today is like load modeling.
Yes,
Okay.
please. Yes,
Uh, uh, I hope. Okay.
yes,
These are all the basic types of loads which are all available in a power system. Okay,
yeah,
these are the
yeah,
basic types of loads which are all available in a power system. Okay, the loads are like here you can see this constant impedance load, constant current load, and constant power load. Okay. What I have, this is the main, this is how we used to model the loads in a power system.
yeah,
Okay, whatever the software we take, this will be the basic details that we will be using for modeling and load. Okay.
Yeah.
Then what is the main difference this constant power load, constant current load, and constant power, constant impedance load that we should know before going for the modeling? Okay. In the right side corner, can you see this? This is nothing but
Yes.
how your constant power. Generally, we used to say it as how zip load will perform depending on the voltages. How this
Yeah.
zip load is dependent on the voltage that we should know before going for the concepts. Okay.
Yeah.
Now what we see in the right side is the graph which says you like here can you see this the one which has a constant power load, this one. Okay. This one, whatever the voltage you have. Okay, whatever the
Yeah.
voltage you have in the x-axis, we do have the voltage, right? In per unit we do have the voltage. Okay, whatever the increase in voltage, what happens is like it will directly maintain the current. It is like voltage and current are inversely proportional. When voltage increases, then current has to go down to have a constant power.
Yeah.
Yes, I hope that concept you don't know
Yes.
about constant power. That is what is happening here. Okay, and why they have stopped at this point is like 0.7. What it does is like when we used to model a constant power load in softwares, what they will provide is like they used to provide some options like below a certain point of voltage. What happens is like your constant power load will change into a constant impedance load.
Yeah.
Okay. I hope you do know about what you say that you have an idea about the constant impedance load. What the constant impedance load does is like it will draw some huge amount of power. So in the during the starting, like inrush of the transform, you know, yes.
Yes.
Like that, whenever the voltage falls below a certain limit, then this load will be converted to a constant impedance load. Okay, constant
Yeah.
impedance load. That is a basic concept that we should remember. Okay. Uh, then what the other part is like, it is the curve for the constant current load.
Yeah.
Can you see this constant current load? Here, what constant current does is like whatever happens. Oh, yes. What happens is like here, whatever happens to the voltage, it will does maintain the current as a constant one. Okay. For real-time examples for constant power load, do you have any idea about what will be the constant power load in a real-time example for constant power load?
Constant power load would be just any load we use at the home.
No, regarding the examples, I will show you. Can you see this for constant power
Yes.
load? For
Yeah.
constant power, our induction motor, which we use in the household equipment or the factories wherever you use induction motor is a constant power load. Okay.
Right.
Yes, at any time what happens is like load takes the constant power irrespective of voltage changes. That is what we
Right.
have seen in the graph also, right?
Yeah.
Whatever happens to the voltage, but it will adjust the current and it will take the constant power throughout the time. Okay, this
Yeah.
is what happens in a constant power load. And
Yeah.
in the constant current load, what are the examples? Is like VFD devices, UPS, and power electronic devices like our charger. There is some we used to have charger for charging the phone, right? We used
Yes.
to have that charger and all. It comes under a constant power load, constant current load. What it does is like it will maintain the constant current
Yeah.
irrespective of the change in voltage. With
Okay.
respect of the change in voltage, it is like here we can say it as it is with respect to whatever the change in voltage, it does draws as a constant current. Okay,
Yes.
this is why we call it as constant current. Okay, for examples, we do have UPS, our chargers, battery, phone chargers, like that we can say. Okay, other than that, what is the other load which is remaining is the constant impedance load.
Yes.
Okay, constant impedance load. Constant impedance load comes under our heaters. We do have heaters in our house, right? That
Yeah.
heaters and all falls under a constant impedance load. What it does is like the impedance remains the same. What do you say that with respect to the square of the voltage, with respect to square of the voltage. That is how the constant impedance load works. Okay, you will get an idea how this power drawn will change depending upon the load after solving some equations. Okay, you will get a clear idea how this constant power, constant current, and constant impedance load works. Do you have any idea about this? How this power loads will take power? Do you have any idea about this before
No.
going in? Yes, yes. Okay. Then what is the equation which I want to show you? Is this equation, this general equation? Can you see down? This is the
Yeah.
polynomial load, which where they have used the. This is the equation they used for the real power. Okay, real. Yes, this is the equation which you have to remember. Okay, for reactive power, the same equation. What they do is like they used to put take out this P and they used to replace it with Q.
Yeah.
Okay, with the Q. This is for this is for without. This is how the modeling will be there for an static. What do you say? Steady state conditions.
Yes.
Okay, for steady state condition, this is how the equation looks. As I said, the constant impedance load depends on square of the voltage, right?
Yes.
Square of the voltage. Here, can you see this? This is the
Yes.
just remember it as Z, I, and P.
Yeah.
Okay, just remember it as Z, I, P. Okay, then you can
Yeah.
Z, I,
I
and
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 P.
P. Okay,
Yeah.
here it
Yeah.
it depends on the square of the voltage. Here it is
Yeah.
proportional, right?
To the voltage.
And
Yeah.
here, yes, here it doesn't depend on the voltage and all. It just
Voltage.
maintains the power
Yeah.
constantly, right? Okay,
Yeah.
this is the equation which you should remember when solving the when finding the power manually. Okay.
Okay.
Yes, I hope you can remember this. And for
Yeah.
reactive power, the same does Z,
Yeah.
I, and P.
Yeah.
Okay.
Square proportional. Yeah.
Yes, it is proportional square of the voltage, and it is what we say that it is directly proportional, and it doesn't depend on the voltage. Okay.
Yeah.
Whatever happens to the voltage, it will adjust the current, and it will maintain the power constant. Okay, this is the equation for reactive power consumption, and it is the equation for real power consumption. Okay,
Yes.
and then the other part which I want to explain, as I said, this is for the steady state purpose. This equation is for a steady state purpose.
Yeah.
Okay, it is not for a dynamic, it is for a steady state purpose.
Steady state.
Okay, yes. With this basic point, we will go for some modeling in ETAP.
Yeah.
Okay, that will give you some more idea about how this load acts and all. Okay,
Yeah.
yes. I hope my screen is visible to my ETAP screen is
Yeah.
visible to you. Yes. Okay, I have took a source. Okay, took a source with the 222 kV capability. Okay, this
Yeah.
is just a grid. Okay, I have modeled just a grid with
Yeah.
with 22 kV, and I
Yeah.
have converted the 22 kV into a 0.415 kV with
Yeah.
1.6 MVA transformer.
Uh-huh.
Okay, with 1.6 MVA transformer. Okay, now I have connected the load here. Okay,
Yes.
now I have connected the load here. Okay, what I have done inside the load is like go inside the nameplate. Here, can you see this? I have took a
Yes.
load of 1 megawatt load. Okay,
Yeah.
1 megawatt load with a power factor of 85.
Yeah.
Okay, with a power factor of 85. Okay, and with this, what I am doing is like I have modeled it as a constant impedance load. Here, can you see this? In the constant
Yes.
EZ, it
Constant.
has
Yeah.
put as
Yes.
100%, right? So that
Yeah.
it does what happens is like it is a constant impedance load. Then
Yeah.
what happens to this? Whenever the voltage changes, there will be what you say that the power consumption will be
Proportional.
a square of the voltage, right? This is
Yeah.
what happens in the system, right? Then for
Yeah.
that, what we do is like we will try to run this simulation. We will try
Yeah.
to run this simulation. Here, what I have modeled a constant impedance load. Okay,
Yes.
and now I will keep this load out of service. Okay, I will keep this load out of service. and I will just run this equation. So run load flow for this particular.
Yeah.
Change it
1.5.
to
Okay.
okay.
Yeah.
I have intentionally reduced the voltage with the transformer. Here can you see?
Yeah.
I have intentionally reduced the voltage with 0.4. Okay.
Yeah. Yeah.
To see the changes, what it is creating here. Okay.
Yes.
Now here can you see this? Now the voltage what is appearing in the particular bus is 0.389.
Yeah.
Okay. Then what is the per unit of this particular point? What will be the per unit here? When we convert into a percentage or per unit, what it will be, how to convert it? Just
Just divide
we have to divide this 389 by
1,000.
no, not 1,000. Here we have the
Oh, 415. Sorry.
415. Okay. Then what is
Yeah.
the voltage which we used to get?
It will be
0.389 divided by 0.415. What is the value we used to get?
0.93.
Yes,
94.
0.937. Okay, it is the
Yeah.
voltage which we will be getting, right? I will
Yes.
take.
Yes. 0.937.
Yes. 0.389 and the other one is 0.415, right? The value which we will be getting is divided by this value. Yes,
Yeah.
0.937 is the voltage which we get, right? This
Yes.
represents this point in the equation, this point.
Yes.
Okay,
Yes.
V divided by Vi. Okay. Then what is the voltage which we have got now? 0.93739. Okay, then what we have to do? We have to take square for this, right? As per
Yes.
the equation. We have, because we have modeled the constant impedance load, right? Okay,
Yes.
this is the only part which is there in the equation. The other part has become zero. Yes. So
Yeah.
y means we haven't modeled it as a constant current or constant power load. We have
Yes.
completely took it as a constant impedance. Okay. So that
Yes.
what we have to do, what we are going to do is like we are going to simplify with this particular point, and we will find the power. Okay.
Yeah.
Okay. Now what we have to do is like we have to take the square root for this, right?
Square.
Okay. Yeah, square. Sorry, square for this. Right?
Yeah. 878.6.
What is the square value? It is
878. Yeah.
878.
878.
Okay.
Yeah.
Okay. Now what we have to do is like what is the real power and reactive power which we have put in there. Real power is 1 megawatt, right? We have took.
Yes.
And
Yeah.
for reactive power, what is the value which we have took? Is
Yeah.
0.62. Okay. These are all in
How do
this
you
is
get
in,
that 0.62?
yes, I will show you. Okay. Can you see here within nameplate?
Yeah.
I have took
Right.
it
Also,
as
you put that right. Right.
yes,
Okay.
0.6. Okay.
Yeah.
How do you convert this if you have the MVA of the particular load and you have the power factor, how can we calculate the megawatt? You have idea about that, right? How can we calculate?
Just megawatt divided by power factor is equals to MVA. Is that right?
Yes, it's supposed to be MVA. Now I'm saying like we do have MVA and we have the power factor.
So
Then
just
how to
multiply that.
calculate them? Yes, we have to just multiply that. Like that, we have found the value for M bar also, right? We do know the cos pi value as 85,
Yeah.
0.85, and if we take inverse, then we can find the angle. Okay, then we can find the angle. With that, if we find the sine of angle, we can get the M bar, right?
MBR. Yeah.
Yes, you can get it. Yes. Yes, then I have took this as 0.62 and I have took the real power as 1 megawatt.
Yeah.
Okay. Now what I have to do, I have to just multiply this with this number, right, for real power, right?
Yes.
If we
Yeah.
multiply with this, the same number only which I am going to get. Okay.
Yeah. Of course. Yeah. That's
Yes,
one.
multiply by with this value, give me 0.87. Here it is in megawatt. it is what we have to do is like it will be like 878. Okay, I haven't multiplied it. So okay, then what we have to do here is like we have to multiply this value with this, right?
Yeah.
Okay, this will be the reactive power value and this will be the real power value. Okay, this is what this should be the value which we should get in the eta. Okay.
Yeah.
Can you see here? This is the value which we have got. Yes.
Yes. Yeah.
This is with respect to constant impedance load. Okay.
Yes.
Now we will try to model it as a constant power load. Okay, constant power load. For that, what I have to do is like I have to change it as 100%.
Yes.
Okay, for constant power load. What I will do is like I will change it as constant power load. Okay, here you can see this. I have here it has taken as 100%. Okay, then I will try. I will try rerun this simulation. Okay, here can you see this?
Yeah, it's getting
What?
complete power.
Yes, it is getting the complete power, right? As I said, it doesn't depend on the voltage and all.
Yes.
Right? It doesn't depend on the voltage and all. Whatever the power we have given here, it will take it as a constant. This is what the difference between the constant impedance load and constant power load. Okay,
Yes, I get it.
this is the value. This is the value which we have put here, right?
Yeah.
1 megawatt and 0.62 mW. Okay, this is what it is taking here. Okay, this is the difference between constant impedance and constant power load. Okay.
Yes.
And then other one which is remaining is the constant current load, right?
Yeah.
Oh, yes. Yes, just wait a minute. I will come, but just wait a minute. Sorry,
No
sorry.
problem.
Yes,
No,
sorry.
no, fine. I will also
Yes.
forward in a
Yes.
minute.
Hello.
Yes,
Can
yes,
you hear
Venkat.
me?
Yes.
Yes,
Yes.
yes. Yes, when we take sessions, we used to close our doors and sit indoors and take session. Somebody comes, then we have to take.
Yeah.
Yes, yes. Okay. Then this is what the difference between a constant current load and a constant impedance load, right? Okay.
Constant
And
power
then
and
I will, yes, constant power and constant impedance load, right?
yes.
Now
Yes.
I will try to model a constant current load. Okay, here there is no option for modeling it as a constant current load. What I can do is like I will take this load. Okay, I will take this load and I will make it as in service. Okay, when we go inside the nameplate, here as I said, here it is the power which is drawn by the particular load that we have to give here,
Yes.
which is 1 megawatt and 0.62 megawatt MW. And the this number determines it is like Z, I, and P. Okay,
Yeah.
Z, I, and P. P1 corresponds to Z, P2 corresponds to I, and
Yeah.
P3 corresponds to P. Okay, ZIP. Now I have took it as constant current flow. Okay, if
Yeah.
I put some values like 0.25, what happens is
Then
like,
it will take the power.
yes, yes, it will take the power. Yes. Can you see this? It will
Yes.
differentiate between them. 25% of constant impedance load, 25% of constant current load, and 50% of constant current, power load. Okay, like this it will differentiate. Now what I am doing is like I am going to take it as constant power load, constant current load. Okay, constant current load. I have kept it as constant current load, and I am just clicking on OK. Okay, now I will keep this load out of service, and I will run this equation. Here, what is the power which is drawing here? It is 935.2 kilo, right? Then what? How we can match that? We can match the same way, right?
Yeah.
0.388.
415.
Yes. Then what we have to do? We have to divide that, right? 0.3 divided by this value.
Yes. Get a.
Yes. So
F12
get 0.935, right? This is the value which we will be getting here, right? Because it is 1 megawatt, right?
Yeah.
Because it is 1 megawatt here, right?
Yeah.
Now what? Yes, we have to multiply this with this value, right? This is what which we are getting here, 935.2. Okay.
Yeah.
Then we have to do the same for this reactive power also. Then what we have to do? We have to multiply this value with this value, right?
Yeah.
Yes, what we get 579.6. This is what it is doing here. Okay. This is the basic modeling of basic modeling of loads. Okay, basic modeling of loads. What happens with respect to voltage? What happens with respect to voltage? This is what that happens. Okay, whenever the change in voltage is there, what happens to the impedance? What happens to the constant impedance too? It will be like a square of the voltage, right? The power consumed. Yes.
Yeah.
Then what happens to the current? It is directly proportional. Okay, it is directly proportional. And the power, constant power load, it doesn't depend on this voltage.
Doesn't depend on it.
Yes, it doesn't depend on anything. It does only, it will maintain the constant power. Okay, whatever may be the voltage or current. Okay. This is about the dynamic modeling of load. This is about the dynamic modeling of load. Okay. The other loads which are this is the steady state modeling of the load.
Static.
Steady state modeling of the loads. Okay. The other type which is available is like there is something called as dynamic modeling of the load. Okay. Dynamic modeling of the load, where we have to use it. Do you have any idea where this dynamic model comes into action? Hello.
It will come in the fault conditions.
Yes, it will come in the fault conditions, or when yes, it will come in the fault conditions, and during load addition or load rejection, like that scenario when happens in a real time system, there will be a change in frequency, right? Throughout the system. Whenever there is a change in frequency, this load has to be changed with respect to the frequency. Okay.
Yes.
That is why they have came up with the model to match that scenario.
What do you mean by load rejection, which means load disconnected? Is that what you
yes,
mean?
load disconnected. Yes, load disconnected. There will be load scheduling, right? After this time, this load will be rejected, like that they will say, right? Like that, when happens is like there will be a disturbance in the system, right? Because if there is a large load, then there will be a large disturbance in the system. Then the frequency gets oscillated, right? Then we used to say like this exciter and governor has to adjust for this load addition, like that they say in electrical. Okay. This is what this is why they have introduced this dynamic modeling of load. Okay. Yes, dynamic modeling of load. Till now, what we have seen is like up to this equation we have seen, right? This is the part which we have seen now. The same goes for the reactive power too. Okay. Now what they have done is like they have introduced the factor with the frequency. Yes, frequency to match the load for the dynamic purpose. Okay. now what it does is like this is nothing but a constant. Okay, kpf and kqf are nothing but a constant.
Yes.
Okay, here you can see this. This is the real power equation constant. This constant typically ranges from 0 to 3.
Yeah.
Okay, this constant typically ranges from 0 to 3. And for kqf, what it does is like this is a reactive power constant, and this typically ranges from -2 to 0.
0.
Okay, -2 to 0. Okay, then how we can calculate the change in frequency, del f, how we can calculate the change in frequency? For that, we can use this formula.
Yeah.
Okay, where change in frequency means at the instant it will be like 50 hertz. Okay,
Yeah.
at the instant it will be in the 50 hertz. When a fault or any disturbance happens in the system, or load addition, load rejection, or something, anything happens in the system, then this frequency will oscillate, right?
Yes.
I'm saying like it has settled at 48 hertz.
Yes.
Okay, I'm setting at 48 hertz. Then what we have to do? Then we have to find the change in frequency, right? What will be the change in frequency?
50 minus 48 divided by 40.
48. Yes, that will be the change in frequency, right? That is how we have to calculate the change in frequency. And if we implement in this, we can match the power consumed by the particular load. Okay,
Yeah.
I will show you that example too.
You cannot do this in the PS card, is that right?
Yes, we can do. We can do.
Okay.
We can do. For just a basic explanation, I'm taking it
Okay.
up for.
Okay.
Okay,
Yeah.
because it is somewhat colorful and it is somewhat easy to match the values. So
Yeah.
that
Yeah.
for basic explanation, I'm taking it up. Okay,
Okay.
and then here what we are going to do is like we'll take this out of service. Okay, and I will put this generator into in service. This part we cannot do. This dynamic part we cannot do in what I say that in PSCAD. For that, what we have to do is like we have to model the complete generator with excitation model. I hope
So
you
you
have.
can't model the generator in the PS card.
Yes, we can model, but we want a lot of details like
Okay.
excitation governor model. That and all we do want. Then only we
Alright.
can perform that. Okay. This is I want to tell you what are the loads which are how to model them in a complete manner, so that I'm teaching this also. Okay,
Okay.
like how this frequency, how this model, how this
All work.
load
Yes.
will
Yes.
work. Okay, now here what I have done is like I have took a generator.
Yes.
Okay, at 22 kV, I have connected a generator with 5 megawatt. Okay,
Yeah.
just for our explanation. Okay, and I'm just other than that, I have took the same system which I have took here. Okay,
Yes.
I have took the same system which I have took here. Okay, now what I will do is like I will just go to transient stability. Okay,
Yeah.
to because it is a transient event, right? Whenever
Yeah.
there is a transient event, then only your frequency will oscillate, right? For that,
Yeah.
what I have done is like I have took this load as an same load. Okay, there is no change in this load. But what I have did here is like I have put it as an polynomial load, as I said before. But other
Yeah.
than that, what I have done is like in order to consider the frequency into our calculation, what I have did is like I have put the kpf value as 1, right?
Yeah.
If I put kpf value as 0, then this frequency term will not come into action, right?
Yes.
Because it is multiplied by this frequency, right?
This factor. Yes. Yeah.
Yes, this factor. Yes, if I put 0, then this change in frequency will not come into impact. Okay. To
Yes.
say show that impact, I have put as an 1 here, and to show the reactive power impact, I have put in this kqf as -1. Okay.
Yes.
Then what I will do is like I will click OK. Then for the we have to add this load. Okay, we are going to add this load. For that, I have created some scenarios here. Okay, at the
Yeah.
fourth second, I'm just going to close this
Close.
breaker
Right.
so that this load comes into picture. Okay,
Yeah.
like this, like that, I have given a scenario here. Okay,
Yes.
fourth second, and I'm just going to close the breaker. Okay, and then what I'm just going to do is like I will run this simulation. Okay.
The software is quite involved. Like PSCAD has like so many fancy buttons.
Sorry.
I said the PSCAD has like so many fancy buttons. It's
Okay.
quite extra.
PSCAD doesn't have this much of fancy buttons, but this do have. That is
ETAB,
what you are
yes,
saying.
ETAB,
Yes,
yes,
ETAP is somewhat colorful.
yeah.
For basic understanding, if you are going to start with power system, I will tell ETAP is a good way to learn basics of power
Well,
system.
once I learn PSCAD, then I will come back to you to learn this.
Okay. I'm not telling you like that. I'm just telling you
No,
if you
no,
are going.
I am serious about it. The next
Okay,
topic I would like to learn is harmonics.
okay.
I am not interested in like load flows and stuff like that, but
Okay,
uh,
okay,
I roughly know how it works. But it's been a long
okay,
time, and
okay,
but yeah,
okay.
this high frequency transient is something like of my interest.
Okay. Right. Yes, then what I have done is like I have run the simulation. Okay.
Yeah,
Now here you can see this load is not in action. Okay.
open.
Now
Yes,
I'm just what I'm doing is like I am just increasing the time. Here you can see this. I am just
yes,
increasing this. Hmm?
yes,
For
yes.
that, what I'm doing is like I'm just I have said like this, at 4 second
One
only this load will
sec.
be coming to action, right?
Yeah,
Yeah, this fourth second your load
yes.
has came into action, right? Now
Yeah,
here you can see this the frequency has dropped, right?
change.
From
Yes.
52 it has dropped to 49.4.
Yep.
Then shall we validate this with how this frequency has came into act with this load? Okay,
Because this is yeah, because this changes.
this is a dynamic model, right? We have
Yeah.
created some dynamic equation, right? So what we have to do, we have to take the same factors which we have took here, right? 1 and
Yes.
0.62. Okay.
Fixed
Other than that, what we have to do,
frequency.
we have to include the frequency. What is the change in frequency here?
As
It is
let me see.
49.4, right?
Yeah. Yeah.
What is the old value, which is 50, right?
Yeah.
50. Then what will be my equation?
50 minus 49.4 divided by 49.4.
Okay. Just calculate it and tell me the values. How the
0.0121.
yes 0.0121.
Yes.
Then what we have to do, we have to multiply with this value, right?
Yes.
0.369 divided by 415.
Yes.
Just check and tell me whether it does match this 879.1 kilowatt or not.
I first need to divide 369 by
Divided by 415. Yes, we have to do that.
0.369 divided by 0.415. Yeah. And then I need to multiply that factor with this. Is that right?
Yes,
And then answer. Yes.
yes. Have you matched that value?
Yes.
879.1 kilowatt. Yes.
Yes. Yeah.
Then try to match this also, 559. What we have to do is like here we have to multiply it with -1. Before that, what we have done with the KPF is we have to here 1 so that we don't have any confusion. But here we have to take it as -1
Yeah.
for
So I do
KQ.
same. I can 40.
Yes.
Sorry, 50 minus 49.4,
4. Yes.
and then divided by 49.4, and then now
Divided.
what I do? Yeah.
Yes.
And then I now multiply this with the
-1.
point first minus one, and then I further multiply this with
1 plus value. 1 plus answer.
yeah. It's 5587. Yes.
Yes. Okay. Now you are
Yes.
you are clear with this concept, right?
Yes.
Okay.
I get this. Yes. Yeah.
Okay.
But
Okay.
it's half the way, when you see the equations, but it's good you when you see the real example.
Yes. That is why I have took this one. Okay. As I
Yeah.
said, we cannot model the complete generator in PSCAD
And
without the
and and
excited governor model.
and in ETAB you can do that simply.
Yes, in ETAP we can simply do that because what the ETAP provides is like it will provide you the sample model of the particular generator with its
So you just input the
governor.
you just input the
Yes.
you just input the power.
Yes, we used to put the sample data.
Okay.
It does provides lot of sample data for this much type of excited and governors.
All right.
Okay. These are all taken. This exciter and governor model has been took from the standard. Okay, IEEE 141 standard. They have to call those values, and they have modeled this exciter and kept inside, so that if you have a project with this type of exciter and governor model, we can simply take this and we can just change the values and we can perform the studies.
All
Okay.
right.
Yes. Yes, this is what happens in dynamics way. What happens to frequency like this, it happens. Okay,
Yes.
and then the other, this is all about the load modeling with
Yes.
respect to the equations and the what is it, that with different types of loads and how
Yes.
we are trying to match these values. Okay, now we are going to the same with this concept, with this base concept, we are now going to PSCAP. Okay,
Yes.
to validate this. Okay, to validate with the same kind of thing. Okay,
Yeah.
before going for that, I will tell you some basic about this load. Okay,
Yeah.
basic about that load. Okay, I hope you can see my screen. Yes. Now here, can you see this? This is a rated real power per phase. It is a per phase value, not it is at a three phase value. Okay, whatever the value which you get,
Divided
for
by
example, yes, we have to put it divided by 3, divided by 3. Okay, divided by 3, and we have to include it here. Okay, and for same for the reactive power also. Okay, this is an inductive power. If you put this value as an plus, it is called as inductive. If you put it with the negative mark in before this is an capacitive.
Yeah.
Okay, this is an capacitive load. Okay, now we are keeping it as an inductive load. Sorry, yes, inductive load. So that I have put it as an 100 mW per phase. It is.
Yeah.
Okay. Then what we have to do is like we have to put the rated voltage. Okay, rated voltage. Rated voltage should be line to ground voltage, not line to line voltage.
Yeah.
So if we have 400 kV, then what we have to do? We have to divide it by root 3, then we have to put that value here. Okay, then here comes the same concept as we have explained in explained before. Okay, here can you see this? There is something called as voltage index for power, right?
Yes.
Voltage index for power. What does this equation tells is like this is same as I said for ZIP. Okay, ZIP. But here what I have to do is what you have to do is like for Z it is 2. Okay, the factor is 2. As I said, it is the square of the voltage, right?
Yeah.
Okay, to determine that, what they will put, it's like they will put 2 here. Okay, if I put here 1, then it is a constant power load.
Yes.
Okay, it is a constant power load. If I put 0, then it is a if I put 1, it is a constant current load. If I put 0, then it is a constant power load.
Power load. Yeah.
Yes, and then the same goes for this Q fact voltage index for Q also.
Yeah.
Okay. Voltage index for Q.
So that's why you're putting 2, 2.
Yes. Wait. Yes.
Yes.
Now, for voltage index, what we have to do, the same goes for this also. If I put 0, it is a constant power load. If I put 1, it is a constant current load. If I put 2, it is a constant impedance load. Okay.
Yes.
And then what is this frequency index? Then what is this frequency index?
Frequency index is basically change in the frequency because of load.
Yes, we have said the term called as KPF here, right?
Yes.
KPF.
Yeah.
And KQF, right? This is called as a frequency index here. Okay, if I put here, it is a frequency index with 1. Okay, as I said, this value will move from 0.1 0 to 3.
0 to 3. Yeah.
Yes, 0 to 3. And KQF will move from -2 to 0.
-2.
Okay. Yes, -2 to 0. -2 to 0. Okay. Hello?
Yes.
Yes, -2 to 0. Now, since we have not modeled it as a dynamic model, I'm keeping this as 0 itself. Okay, 0 itself. Then what we have
all 0 means is constant power load, right?
Power. Yes, constant power load. Yes, you got it. Okay, and then what is the other thing is like we have to set the frequency, fundamental frequency for this.
Yes.
Okay, fundamental
Yes.
frequency is 50 hertz here. Okay, then if you want to display the details of m megawatt and m megawatt
Yeah.
outside, then you can keep it as yes here.
Yeah. And here
Okay.
we don't need to put the any frequency index and power index.
Yes, because as I said, we have not modeled the exciter and governor model, right?
Yes.
There
Yeah.
is no such thing as exciter and governor. So that
We
with this
just put as
model,
a voltage source.
we have just modeled it as a voltage source. It is a constant voltage source. It will maintain 1 per unit at this cost.
Yes. Yes.
Okay.
Yeah.
And then what I have to, yes, that's it. That's it. That's the input which we have to give
Yeah.
for the load. Okay.
Okay.
This is different kinds of loads I have
Yeah.
constructed for your basic understanding. Okay.
Yes.
This is a modeling of constant resistance. It is an inductive load. Okay, it is an inductive load. Okay, we will start from here. We will start from here. That will be good. It is an inductive load.
Yeah.
Okay, it is a modeling as a constant power load.
Yes.
Okay, this is what now we have seen, right?
Yeah.
Here, what it will be inside this, what it will be look like. It will be there will be values for megawatt and megawatt. All the other values will be zero, right?
Yes.
Okay,
Because it
here you
won't
can,
depend.
yes,
Yes.
here I have kept all those values as zero, right?
Yes.
Okay,
Yeah.
and other than that, there is something called as capacity load, right? As I said before, I have said about capacity load, right?
Yes.
Here, can you see this? I have modeled the capacity load. Okay,
Yes.
modeled as a constant power load. What I have to do, I have to just put a negative mark before the M1.
MVR. Yes.
Yes. Other than that, other factors will be same as zero.
Yeah. Yes.
Okay,
Yeah.
then the other next thing is like inductive
Yeah.
model, modeling as a constant current load.
Yes.
Then
So in
how?
this you will put a ZI. So you will put 1 1.
Yes, I will put 1 1. Okay,
Yes. Yes.
then the same goes for the capacity also. If I go
Yes.
in, there will be negative mark in between, and I will put
Yes.
1 1.
1 1.
Okay, yes,
Yeah.
and the next one is like inductive load modeling as constant resistance and reactance. How to model
Yeah.
this?
A inductive load.
Ah,
So you put basically square.
yes, basically square. Resistance and reactance comes with impedance, right? I
Yes.
have I have put it. What I have to do? I have to put 2 2 here. 2 2.
Yeah. Yeah.
Okay. And
Yes.
then the same will I have modeled with that capacity load also. Then
Yes.
this one is much important. Modeling as a constant resistance and constant inductance. How I have to model this?
Inductive load minus constant resistance. I think you put just a square
No.
and
For constant
yes,
inductance, yes, I have included this -1,
the
right?
MVR. Yes. Yes.
Yes, this frequency index. Can you see this?
Frequency index
Frequency
for the
index as
yes for
-1.
the reactive
Okay.
power. Yes.
Yes. Now what it does is like whenever the frequency changes, it will
Maintain.
constantly act as a constant inductance.
Yeah.
Okay.
Yeah.
This is for your example. Okay, this is for your example. Okay. This is.
And where we are going to use this type of load in like this study, the one I'm going to face.
Where you are going to use is like we will be doing some studies called as temporary over voltage studies, right?
Yes. Yeah.
Temporary over voltage studies. It is like
So
what we
it
use.
is. Yeah.
Yes, yes. What they will do is like we used to do reject the load like that
Yes.
scenarios. We will add this load, and what
Yeah.
happens to this voltage, steady state
Yeah.
voltage,
Yeah.
that we have to see with respect
Yes.
to load rejection and load addition, and by
Okay.
creating a fault uh,
Yes.
with the fault with load rejection, like that cases and all we have to perform, right?
Okay.
So
Okay.
that for that what we have to do is like we have to model this load.
Yes.
Okay, we have to model this load. Generally, what type of load we used to model is like we used to model it as a constant power load.
Yes.
Okay, to give to give the idea about how this load acts. For that only, I took this much of time to explain it. Okay.
Yes. Yes. Yes.
Yes. Yes.
It's clear.
Then yes. Thank you. It is clear, right? Then
Yes.
what we have to do is like we will try to match the same as we have did with the ETAP using PSCAD. Okay. Hello.
Yes, yes, I can hear you. Yes.
Yes, yes. We will try to match the same as we did with the ETAP with the
Yeah.
PSCAD. Okay.
Yeah.
Now what we will do is like I have took a source. I have took a source.
Yeah.
This source modeling which we have used for source
Yes.
modeling example for you. Okay, that is the same source I have took here. Okay.
Yeah.
Now what I am doing is like I will put this voltage as 400 kV. I will put this voltage as 400 kV. Okay.
Yeah.
400 kV and with the phase as 0. Okay,
Yeah.
with the angle difference as 0, and I have modeled this bus with the 400 kV and I have put a multimeter here. Okay,
Yes.
I have put a multimeter here. In this with this multimeter, what I am doing is like I am just measuring
Measuring
the power,
active and reactive power.
reactive power, and then RMS voltage here.
Yeah.
Okay, RMS voltage in digital format.
Yes.
Okay, RMS voltage in digital format. Then other things what I have to do is like I have to put this frequency here. What is the
Yes.
frequency of the system? Okay, if you put 60 hertz, then it will show wrong values. Okay, this
Yeah.
is whenever you use meters, you have to change this as 50 hertz. Sorry,
Yeah.
60 hertz. 50 hertz or 60 hertz that you have to change. Okay, depending on the system frequency which you have.
Yes.
Okay, and what we have to do now, we are trying to measure real power, reactive power, and RMS voltage. Then what we have to do, we have to put this some names for this meter, right?
Yes.
I have given the signal name as real power,
Yeah.
real PO, and reactive power REAC and voltage. Okay, okay. Now what we
Yes.
have done is like we are just we don't have any option to get the RMS voltage. Sorry, RMS
Yes.
real and reactive
Power.
power here. Okay, real and reactive power here. So, but we have options to get a RMS voltage, but we don't have any option for getting RMS power flow. So
Powers.
that I
Yeah.
have put an RMS meter in middle. So that I
Yes.
have put a 50 hertz here, and I am just measuring the power here.
Yes.
Okay, this now I have modeled it as a constant power load. Okay,
Yeah.
constant power load. Okay, now I will just run the simulation.
Yeah.
Okay, now I will just run the simulation. If you want to see these values as within 900, you can double click on this
Yeah.
y-axis. Okay, for your EC view, here you can see this y. Change this y max as 950. Okay,
Yeah.
950, and just click OK. Now here
Yeah.
you can see the values as 900. Okay. Now here can you see this the value which it has came is 900.541.
Yes.
Okay,
Because it's for the
since
maximum power.
yes, maximum power because it is a constant power load, right? It is
Yes.
showing the values for three phase. Okay, it is
Yes.
showing the value for three phase, but
Three
here we
phase.
have put the value as single phase, right?
Single
So
phase.
only
Yes.
it is showing 900, right?
Yes.
As we did before in the ETAP, like that also
Yeah.
we can match it here also.
Yeah.
Okay, with the voltage. With the voltage here you can see this, the voltage is 384.07.
Yeah.
Okay, we have to just divide it by 400, which is the
Yeah.
base voltage. Okay,
Yes.
384 divided by 400 will give you 384.07 divided by 400 will give you 0.96, right?
Yeah.
Since it is a constant power load, what it does?
Then we
What
multiply that.
multiply with?
Right. We just multiply
Yes,
with that. With that
uh,
factor.
with this power, right?
Yes.
Which is nothing but here what it is?
300.
300. Here it will be 900, right?
Yes.
It's 900, right? Here.
Yes.
What we are getting?
Oh, sorry. So I do 384.
Yes, 384.
0.07
We
divided
don't need
by,
we don't need to take voltage, right? Here.
yeah,
It is a constant power load, right?
yeah, yes,
Whatever happens to the voltage, your power remains the same, right?
remains the
Here you
same. Yes,
can see, here you can see this, there is 900, right? 900.
yes, yes.
And there is 300, right?
300 reactive. Yes,
Okay. Now we will change this factor to 2. Okay,
yes.
now it will act as a
A constant impedance load.
constant impedance load. Okay, constant impedance load. Then now I will run the simulation.
Now the power will be different.
Power will be different, right? Because now it does depends on the square of the voltage, right?
Yes,
Can you see this? Now here it
yes,
has changed to
right.
835. With the
Yes,
with this value we can match that also. 385.396 divided by 400 will give you some value. That value
yes,
we have to square it, right?
yes,
That value we have to square it, and then we have to multiply it with 900, right?
yes.
Then it will be 835.48, right?
5.48. Yes,
This is the value which we are getting here, 835.48.
yes,
Okay. The same does goes for the reactive power too. Okay.
yes,
Like
yes,
this, you can model the real and react different types of loads. Okay,
yes.
real constant power and constant impedance load, like
1885.
that we can do this. Okay. This is all about load modeling, Himanshu. Okay, I hope that is clear for you.
Yes,
Okay.
yes. This is clear.
Okay.
What about that capacity, power, and other stuff? It will same behave like just as the same as the
Yes,
impedance.
so it will behave the same. Like if you put here minus
Like,
100,
yes,
then what we have to do? Then we have to run this simulation, right?
it's a basically constant impedance capacitive load.
Yes, constant capacity load. Yes.
Yeah. Is there a note somewhere or written somewhere like how do I keep this in memory? Like you done there inside these boxes, like impedance with, yeah, I understand, like a constant impedance and constant power and a constant current one, but
Oh
like
yes.
you model these various options, yeah, like how do I
This
put
this
my sign, yeah,
this this
yeah,
this one. How to put
yeah,
this one?
yeah,
Okay.
yeah.
For that, what you have to do is like you have to go inside components.
No,
Okay.
no, i
Ah.
i know how to put that block, but what I'm saying
Okay.
is how how do I remember, like where where you put inductive as a minus and capacitive and stuff like that in these various options? Do you have any written notes anywhere on these? Yeah,
Okay.
I'm
Okay.
talking about those options. Yes.
Okay. Okay.
Because
This.
it will go, current and voltage and impedance I will remember,
Okay.
and
Okay.
capacity perhaps I will remember, but just for a
I
memory I
will
was
share
asking.
this PPT, man.
Okay.
Okay, this PPT, I hope this PowerPoint will help you to remember those
You can
values.
also maybe send me that file as well, the one you prepared on your screen. I will,
Yes, yes, that I will send you. That I will send you.
yeah,
Not a issue.
I will
Yes,
keep that as a
no problem at all.
reference
Yes,
because, over the time sometime I forget. So it's
yes,
good
yes,
to
we
get,
will forget
yeah,
something. Yes, yes, yes. It does
yes,
happen. Yeah, it does
yeah.
happen. Okay, I
And
will
then
share
if,
this
if I have
file.
a file, then yeah, I will remember, like, okay, this is, and
Okay,
I will perhaps put some notes somewhere.
okay, okay. Yes, I will send this model to you. Okay.
Yeah.
Yes. Uh,
Yes.
That's it about load modeling, which I have planned today. And the other simple modeling is like I have planned for a shunt reactor modeling. Okay,
Yes.
shunt reactor modeling, which is very, very simple. Okay,
Okay.
so I have to keep that today's.
One second, Venkat. I will come in
Yes,
one.
yes. Okay, okay, fine, fine, fine.
Sorry, mate.
It's not a thing.
I have a young boy in the house, so he just sometimes just
Yes, yes.
try to break the things.
Okay.
Yes.
For reactor modeling, you have to get data like this technical data sheet for
Okay.
reactor. Okay.
Yes.
Like this technical data sheet, we have to get it from the customer.
What this
Okay.
data sheet is for in particular?
This is for reactor, shunt reactor.
Yes.
Okay. For shunt reactor, if you have any reactors, we have to get it from the customer. Okay. The other things are like we have to get the VI characteristics of the particular shunt
Reactor.
reactor. Okay,
Yes.
for shunt reactor. Okay,
Yeah.
uh, that we have to collect it from the customer, like magnetizing curve of the particular shunt reactor. Okay, and the other details is like when you are going to model a shunt reactor, the other details which we have to get is like we have to get the what we say that we have to get the bushing capacitance value. Okay,
Okay.
bushing capacitance value that we have to get, and
Yes.
other things is like we have to get the other details. I will show you. I will show you.
So we cannot get that busing capacitance value from anywhere else.
Yes, we can get that value from reference test like this. If they have any done any test for the particular reactor, that value we can get from it. Here, can
Okay.
you see this? There they have
Yes.
given the value for the capacitance
Yes.
value they have given. This is for the bushing, and for bushing they have given the
So,
capacitance value, right? For
okay.
winding also they have given the capacitance value, right?
Right.
Okay,
So you get
winding.
strictly that from only from the manufacturer
Yes,
or whoever is your
yes,
client.
from the manufacturer only we can get this value. Other
You
than
can't
that,
assume so like something off shelf like from standards and
yes, for this, what he said that for reactors we cannot get any values. For transformers we can get some values,
okay.
but for transformers, specifically for two winding transformers, we can get values. But if we have any three winding transformers or auto transformers, then the customer have to provide the values. Okay,
Okay.
we
No, you
cannot
know
get.
why I'm asking because sometimes client just says like assume, and then you're like, what to
No,
assume? You
no.
need to tell
We,
something.
yes, we have to tell some values, but we have to stick to this. We cannot assume these values.
Okay.
Then what we can tell is like then our accuracy of our model gets decreased, right?
Okay.
Without that data. Yes, then with assumption data. With assumption
Yes.
data, what we can do is like if we have done previous projects, the from previous projects we can use that same data, but we
Yeah.
cannot tell them like this is from the standard. We cannot go and argue with them, right?
Okay.
Because they won't accept that values and all.
Yeah.
Because for that only I'm telling you like we have to stick to this. We have to
Yeah.
get the capacitance value from the customer, bushing capacitance value, winding capacitance value, and
Yes.
other than that, what we have to get is like uh, we have to get the coil
Okay.
resistance value uh, of the
Reactor.
reactor. Okay, and other than that, what we have to do is like we have to get the insulation
Okay.
resistance value to completely model the what we say that to completely model the reactor in for different kinds of studies.
Okay.
Okay, I'm just to provide giving you information like these are all the amount of data which we have to collect it from the customer for particularly modeling the reactor. Okay,
Okay.
for particularly modeling the reactor. Okay,
Yep.
then other than that, we have to model this capacitor as a saturable reactor, right? For that, what I have done is like I have took a saturable reactor from this model. Mm,
Okay.
just this take for a minute. Can you see this? There is something called a saturable reactor.
Saturable reactor. Yes.
Yes, that reactor I have took it from there and I have put it here. And then
What it does, saturable.
saturable reactor means it is like a transformer, right?
Okay.
After giving some particular reaching some particular voltage, what it does is like it will draw some huge amount of current, like
Current.
interest
Yes.
current. Yes,
Yes.
right. Like that it does happen. That is what we call the saturation, right?
Yes.
The like that we have to get that information from the customer.
Yep.
Okay. Then we have, for modeling purpose, what we have to do is like just to give a name for the particular reactor.
Yeah.
Okay, whatever name you can give it. Then we have to specify in which format you are providing the data.
Okay.
Okay, whether you are providing the VI characteristics or we are providing the uh, information in I lambda format.
Okay.
Mostly we will stick to this VI characteristics
I,
itself. Most of the customers don't provide this I lambda value. They will provide only this VI characteristics only. Okay.
yes.
And then the other option is like we do have two options, like whether we can provide the data inside this box itself, inside
Yeah.
this box itself. Other than that, what option we do have is like we can give it in the data file format.
Okay.
Okay, data file format means we can create the data in the notepad format.
Yeah.
Okay, notepad format. And with that notepad name, we can, if we put it here, it will take data from the particular notepad.
Okay.
Okay, from the particular notepad. That part I will show you when we come to modeling of surge arresters. Okay,
Okay.
surge arrester we used to put the values from the notepad. At that time I will show you how to get the values from the data file. Okay.
Great.
What is the basic thing is like we have to create a data, we have to select data file here and put the particular data file name. What we can say is like we have to put the particular just wait a minute. Here it is raining heavily, so
Okay. No problem.
I will unplug some things from the from the socket for for safety purpose.
Yeah.
Yes, yes, yes. What we have to do is like here we have to choose it as data file, and we have to
Yes.
give the name of the particular notepad file which we have created in a particular location. Okay,
Yes.
particular location, that that data file has to be inside this particular folder where you
Yes.
have saved this file. Okay, here
Yes.
you can see, can you see this? Now I have created new folder here, and inside
Yeah.
that folder I have all those files. Okay, here you
Yes.
have to put that notepad here. Okay,
Okay.
here you have to put that notepad here, and with that
Then link
extension,
it.
yes, you have to link it here.
Yes.
Okay, with that same extension, we have to link it here, and it will get data from there. Okay,
Yes.
but now we have put the values in the table itself. Okay, in the table itself, the table itself. Okay, now what we have to do is like we have to give go for data, and now
Yeah.
we have to put the kV voltage. What is the voltage of this particular reactor? Okay, that
Yeah.
we have to put. Okay, what is the base voltage in per phase we have to enter.
Yeah.
Okay, where we can get this value? We can get this value from the technical data sheet. They might have provided the value as rated voltage of the winding, right? Here can
Yeah.
you see this rated voltage of this winding? With this,
Yeah.
if we divided by root 3, we have to put it that value here. Okay, and then the other value is like we have to get the
So
arm.
that's again RMS phase to neutral,
Yes,
right?
yes, phase to neutral. Yes, RMS voltage.
Yeah.
Here also the same concept. Here they will provide the per phase current only. Okay, we can directly take it from the here you can see this. There it is
Directly.
nothing but a per phase current only. Okay,
Yeah.
here you can get this current 86.6, and we can
Yes.
directly enter here. Okay, we can directly enter here. Okay, no need to divide by root 3 or something and all. Okay, we can
Yeah.
directly enter here. And for base frequency, we have to keep it as 50 hertz. Okay, it
50
depends on the network frequency. Okay,
Yes.
and other than that, as I said, we have to give the details in per unit format like this.
Yes.
Yes. RMS current and RMS voltage like this we
Voltage
have to create. Where I have took this value?
from line graph.
Yes, from the saturation curve, which I have got from the customer. Okay, from this graph. Okay, here you can see this up to 1 per unit.
Yeah.
My current and voltage are in phase. Okay, what do you
Yeah.
say that it is linear? It is linear.
Yeah.
Okay, after
Specifically
some
between two.
yes, after 1.3 per unit of what do you say that after 1.15 I hope it will be 1.13. It will be 1.3 I think so. After 1.3 per voltage, what it does is like it has what do you say that it has gone out of linearity, right?
Yes. Yes.
Okay, with these values, we have to take the values from there, and you have to enter here. You can see this up to 1 point per unit. I have put it 1.1 per unit like that value, right?
Yeah. Yeah.
Okay, like this you have to create the table.
Up to what you put the full thing, right? The
Yes,
linear
I
and
have put
non linear both.
yes, I have gone up to 3 per unit, right? For current. Here in
Yes.
the graph, in the saturation, you can see this, they have given the value for 3 per unit. So that I have to stick to 3 per unit, up to 3 per unit.
Yeah. And
Okay,
on that
if you have large number of points, like if you have 15 number of points, then what we can do is like we here we don't have any option. We have to completely go for this. Sorry, go for this data file format
data
only.
for
Yes, data file
when you
format.
have 15 point.
Yeah, if you have above, what we can say here, we do have 10 points, right? When we
Yeah.
have above 10 points, then we have to go for this data file format only. Other
Only.
than that, there is no option.
And you cannot skip any
Sorry.
point. You cannot skip leave any point. Say if I put a point one RMS point three, right? And
Okay,
then
okay.
after that, I know it's linear, and I just directly put point three. I just leave
Yes,
point two,
that is what
whatever.
I have done. That is what I have done here also. I have generally took 3, 6, and 9. Can you see here? 3, 6,
Yeah.
and 9. I have took it here, and I have directly jumped to 1.2 per after that.
Yeah, that's what I'm saying.
Okay.
As long as it's linear, it shouldn't matter.
Yes, yes. It is, as long as it is linear, we can put any values and we can match it here. But after
Okay.
linearity, it depends on the number of points here.
Yes.
Okay, it
Yes.
depends on number of points.
Right.
Okay, this is how we have to model we have to model the reactor. Okay,
Yes.
as I said, this is nothing but the coil resistance.
Yes.
Okay, this is coil resistance. I have to model it another what you say that with parallel to this.
Yeah.
I show you. Sorry. Okay, parallel to
Yes.
this, what I have to do is like I have to put what they say that I have to put the insulation resistance. Okay,
Yes.
insulation resistance are parallel to this. Okay, and then the other thing what we have to do is like we have to put the bushing capacitance value,
Yeah.
which we have got from the customer.
Yes.
Okay, to ground, boosting capacitance to ground. Okay, like this we have to model, and yes, that's it about the reactor
So this
model.
this this only small part is reactor model. Basically, that particular zoomed in area, right? This
Yes,
capacitance and then
yes,
this stray
this
and
stray cap.
resistance
This is
and
nothing but a stray capacitance. We say it as
yeah.
stray capacitance, like bushing capacitance. That is what we say.
Yeah, but in that sheet you got couple of values, so you just put one values here.
Yes, yes, yes.
How did you
Okay.
decide this value from the sheet?
Yes, we can. Here we can see this. There is something called as bushing capacitance value, right? For bushing.
Yeah, yeah, but yes, but what I'm saying is you got values see but it's different, it's not different per phase like UVWN is like
Yes,
423,
yes. Here it will be the same value. Here, this is a testing sheet which they have done in the site. So that
yeah,
what they have to provide is like they have to provide what is the capacitance to bushing capacitance for each and every phase. Okay, for each and
so
every phase
you just
they have.
you just added it in the series, is that what you do?
No, no, no. What I have done is like what I should have done is like I have to took this value only.
Okay,
Can you see
423
this
only,
423 value? Can you see
right?
this? Yes,
Yes.
423 value. That value you can take anything like
Yeah,
here.
one of them.
One of them you can take it.
Yeah, this is
Okay.
a per phase logically. So in
Yes, sir.
reality, means what say it is not identical, right? So one phase is like 423.2, other one is 423.1, and other one is 422.9. So
Yeah. Yes, sir. Yes. Yes.
Okay, okay, I
Yes.
get it. Understood.
yeah.
Yes. Yes, sir.
From losses, how to find out the resistance that we have covered? No, Venkat, sorry, I have joined just now, so
Yes, sir. Yes, sir.
you cover.
For losses, if we have got this type of data sheet, they might have given the values directly, rightly. Yeah. coil resistance. Can you see this here?
Yes.
This is for the winding resistance. They might have given the values directly here.
Yeah.
For each and every winding, what is the resistance? They might have given these details directly.
Okay. And
you got the point. No, this will come only when the reactor is manufactured and tested at factory.
Tested at factory, yes.
Yes.
So, but like I mean, what say? Sometimes you need to do the insulation coordination at the beginning of the project itself. By the time you may not have this. You got the point, no? By the time you will be having only data sheet. Okay. So from that point, like means what say how to take this resistance value also we have to know. Okay.
Yes, sir.
That's what I have asked you.
For that, what they will provide is like here they have not provided the losses. Here they have provided losses, sir. 175 kilowatt as losses. This is the total losses, sir. It does takes into account to both the losses, right? Like we have two losses, right, sir? Like
this
core
is reactor,
losses.
no?
Oh yes, sir. This is reactor.
Yeah, this reactor means from 175 kilowatt. If that is the same transformer, is it the same reactor for the FAT report as well as this data sheet, or two different?
Yes, sir. This is the same report.
Probably from this 175 kilowatt, you will be able to find out that resistance.
But the resistance won't be matching. What I say is like here they have given the value as 2.2344. Okay, but when we calculate with this value, what we used to get is like it is like I square R, the general formula will be. So I square. If we put that value, then what will be the value which we get is like 175 kilowatt. Divided
we
by.
are seeing only the PDF document. If you open the Excel sheet,
yes, sir.
And I mean, if we get take the losses, yeah. So 175 kilowatt is the loss, correct? No, that is 3I square R, correct? No.
Yes, sir. Yes.
So I we know rated current of this reactor is known, correct? No. Yeah. So means what say 175 kilowatt means what say so 3I square R. So 175 divided by 3 into 86.6 square, we will get the losses, right? Divided by into 1000, of course, because that is in kilowatt.
Divided by 3, we have to put, right, sir?
Yeah, 3 into I square R. So I square into again H9, yeah, power 2, yeah, whatever it is. Okay, fine, yeah. Into 1000 is the resistance.
Yes, sir. Yes, into resistance.
So this is probably means 175 kilowatt. Probably means you should have multiplied by 1000. Yeah. So this is the resistance value. Is there any change there? Means is it not really matching with that?
It is really not matching, sir. Here you can see this. This is nothing but 2.23. This is for the winding they have given.
No, this one is like is it I mean the reactor is a star connected, correct? No.
Yes, sir. It is star connected. Yes.
So means what is it? Can you just go to there? Like what is the reactance value? Can you just go to the above formula?
Here, sir. Here. Yes.
Yeah, 3I square R has to be the same one, correct? No.
Yes, sir.
So means from where you have taken the rated current is 86.6. The losses are not matching, then probably means what's the approach which we are using is wrong.
Here, can you see this, sir? 86 point.
No, but what's the reactor rating?
Reactor rating is 60 MW.
Okay, for 60 MVR, 60 divided by root 3 into 400 is how much we are getting? Divided by root 3 into 400 is like 86.6. That's right. So what's the current which we are getting is right. 86.6 amps is what we are getting. That's perfect. Okay, all right. Go back to this data sheet.
Yes, sir.
Yeah, data sheet. Let's finish the. Means is it the same project one or it's two different one? That's my question. I guess the data sheet you are referring to some other projects, and the FAT report what you have is something different. Is my understanding right, or still different?
So this is what we have got it for the particular
yeah,
project.
This is 60 MVR, rated frequency is 50 Hertz, rated voltage is 400 kV. This is a shunt reactor for one of the project which is manufactured by GE, correct? No?
Yes, sir. Yes.
Do we have the data sheet for the same project? That's my question.
Then
is it the same project or is it a different?
Same thing. That's what he's saying.
It is GE Turkey.
Okay, fine. Yeah, come down. Rated voltage, rated frequency, vector group is matching, cooling is matching, everything is matching. Yeah. So rated voltage is 400 only. Highest voltage is 420. That's great. That's perfect. Yeah. Go down. MVR. Yeah. Ohms per phase. Here itself they are giving like means what to say. 2600. That is a reactance. Where is the resistance?
Yes, sir. This is what they have tested also.
No. This is a reactance, correct? No.
Yes, sir. This is reactance. Reactance also they have tested and they have given the value.
Reactance we can easily calculate, correct? No. Reactance calculating is quite simple. Like MVR we know, voltage we know. From there X we can calculate. That you know how to calculate, right? This 2681 you have manually find out, right? This 2666.67 you find it out, right? Or
okay.
No, my question, Himanshu, have you got the point how you have arrived this 2666.67 from 60 MVR and 400 kV?
Yeah, you divide the MVR divided by kV. Yeah.
Yeah. Okay. So this is clear, no? Like means what say rate is 60 MVR, correct? So root 3 into VI is basically means MVR. So means what say otherwise like V square we can write like V square by XC also. So I mean what say if you divide this by means what say
root 3
0.4 square, then probably means what say you will get the resistance, correct? No?
Yes.
Yeah. So probably means what say try once. Why I'm saying this because like you need to probably match it. Venkat, can you just try to match this MVR 60 MVR with the rated voltage? Can you just find out the reactance like that is 2666 ohms?
This is what you are asking.
Yeah, 60.
Yeah, MVR. Yeah. Voltage we know.
400. Yes, sir.
Yeah, that is kV.
kV.
Yeah. What we need to find out is X, the reactance value.
Yeah.
Correct, no? So I mean, what to say? We know like means reactive power Q is equal to V square by X. Correct, no?
Yes, sir. Here we have to.
So X is equal to.
X is equal to
V square by MVR. Correct,
V square by MVR. Yes.
Yeah. So equal to
400.
400.
400 square.
Divided by 60.
Here we can match it like this.
You got this point, no?
Yes.
So this is the reactance, but means what say we cannot really go by the same principle for the resistance. For a resistance, like means what say you know what's the current which is flowing through that is 86.6 amps.
Yes.
Correct.
Yes,
and probably you know like means what say 3I square R is basically the real power loss. So the real power loss is given. Say example either efficiency is given or real power loss is actually given. Then probably from there you can means what say back work this R and you can find it out.
Yes.
Yeah. What is the losses now? 175 kilowatt. Current is known 86.6. So means the resistance 3I square R is means what to say this value 175. So 175 divided by 3I square you will get the resistance that's the value. Yeah. So this value will be there in the data sheet again or a FAT report. Can you just go to the FAT report, Venkat, to match this resistance R 7.7?
Sir, here we can.
This is only reactance and inductance. There is no resistance. Can you just look at the losses? Or somewhere they might have given the FAT report. They have definitely measured the efficiency or losses. Yeah, DC losses. Yeah, you can find out resistance they have. Yes.
Here, can you see this?
That is,
they have given us 2.215. That is what the value they have given.
yeah, correct. The total losses is 60 kilowatt. Correct, no?
Yes, sir. 60 kilowatt.
Yeah. So where they have given like means was they have given the maximum value as something, but the actual value is 59.118.
Yes,
So
sir.
from there, like you can easily find out the resistance. So like means what say it's crystal clear as well. Like means what say the resistance they have given, the DC losses they are finding out. That's simply straight away I square R. So each phase they are putting I square R, I square R, I square R, and they're summing up together. So I is known, R is known. So means what say from 60 kilowatt you can find out either this 2.625 or from 2.625 you can find out the loss is 60 kilowatt.
Yes.
Himanshu, are you probably clear?
Yeah.
60 kilowatt is like three phases, so 20 kilowatt, 20 kilowatt, 20 kilowatt. So from 20 kilowatt you can find out the resistance per phase, right?
Yes.
Yeah, right. Yes, Venkat, please go ahead.
Yes. Sir, that's the plan I have took, sir. We have planned to model a load here and the reactor. We have completed. The verge of completing the session. You have came, sir. Yes.
Okay. What are the things we have covered so far? I mean, sir, not today. I am asking. Probably from the overall.
Sir, we have completed modeling.
No, I'll take it from him. Like what
Okay.
he.
All right, he was asking
Yes,
me.
yes.
So, yeah, we learn like source modeling, load modeling, and transmission and cable.
Yeah.
And he also gave me some extra idea about how to validate Faraday effect from another software or PSCAD itself, and various type of bus bar schemes.
Okay.
I think this is it, Venkat, or I'm forgetting something.
Yes,
I guess like a transmission line modeling you might have discussed in deep, right? Lumped parameter, distributed parameter.
Yes.
Yes, we have. Yes.
Okay.
Cable and transmission line. I already had some, little bit idea.
Basically.
Yeah. I don't do the like EMTP based modeling, but I was aware of various model like JMRT, Burgeon, NODA and stuff like that. So yeah.
Right.
It was yes.
Okay. Great. Okay, then if you are done, probably today, Venkat, we can wind up the session. That fine. Himanshu, if I am available tomorrow, I am not really sure. If I am available, I will ping you. Okay, we can have maybe a 2-hour session. Tomorrow morning, I will ping you.
Yeah. If you are available, you can ping me tomorrow morning, and we can have one. Yes.
All right. Thank you so much.